Hello, this is an entirely new topic which we are going to start now about principal component and factor analysis. These topics are very important when we are working with data with huge dimensions, when you have lots of predictors and when those predictors are correlated with one another. Recall the concept of multicollinearity when we were discussing linear regression. So when we have lots of variables or lots of predictors, so to say, and they are correlated with one another, so sometimes it's good to reduce the dimension of the data. And this principal component analysis and factor analysis can tell us how can we reduce the dimension of the data. But before we go on to discuss about the topic, let me just give you a very brief idea about a very important concept in general, the unsupervised and supervised learning. In the supervised learning, we observed both a set of features x1 to xp for each object, as well as the response or the outcome variable, right? And the goal is then to predict y using x. So you observe your predictors and you observe your outcome, and your target is to predict your y based on your x values, and that's what we call supervised learning, because y somehow we are supervising the projection of variables, so to say. Somehow we supervise how y behaves with respect to x, right? For instance, if you are asked to predict a binary outcome from a data set, you have a very well developed set of tools at your disposal, such as logistic regression or linear discriminant analysis, classification tree, and so on, so forth. So these are your supervised learning, because here you look for response depending on your variables. Either you have qualitative variables or quantitative variables, or either you have qualitative response or quantitative response. But in unsupervised learning, we observe only the feature effects. There is no y involved in unsupervised learning. We are not interested in predictions. We do not have any association with the response variable y. We only are interested in x in the set of predictors. We wanted to know how x evolves, what are the structure of x, how x depends one another, how it evolves, how it behaves, right? So unsupervised learning is often performed as a part of exploratory data analysis. There is no response involved in unsupervised learning, and we are only interested in the behavior of x variables. And if you do so, then we call this as unsupervised learning. And the goal of the unsupervised learning is to discover interesting things about measurement. Is there any informative way to visualize the data? Can we discover subgroups among the variables? For instance, among the observations, you have lots of variables, lots of predictor variables. Do you see some kind of grouping going on among the variables? Can you classify them within the set of predictors? There is no y here, but within x, can you classify them in different groups? And you will see some of the examples today. So we discussed two methods to do these jobs, like principal component analysis and factor analysis. And principal component analysis is a tool used for data visualization or data pre-processing before supervised techniques are applied. For instance, you have, now read this sentence very carefully. Before going to do a supervised techniques, we do data visualization through principal components, right? Suppose that you have multicollinearity in a data. Your predictors are correlated with one another. So what you do, you run a principal component, and then once you're done with your principal component analysis, you use that principal component result to do your regression, which is a supervised technique. And if you do so, then your data or your final result will not be affected by multicollinearity, because somehow you removed multicollinearity through principal component analysis. So before running a supervised technique, we run some sort of unsupervised learning methods to somehow pre-processing of a data. And once we are done with that pre-processing, we used that result for our supervised techniques and whatever they can be: regression, logistic regression, discriminant analysis, classification, whatever. Factor analysis is another method, a broad class of method for discovering unknown groups in the data. Do you see a common factor in a data in all the variables. And if you do so, just try to identify that common factor in the data. And that's what we do through factor analysis. However, there are some challenges associated with unsupervised learning. For example, unsupervised learning is more subjective than supervised learning. There are no simple goals for the analysis. We somehow are exploring the data. There are no prediction going on, and we're not interested in predictions either. But techniques for unsupervised learning are of growing importance in a number of fields. For example, subgroup of breast cancer patients grouped by their gene expression measurements, for instance. Groups of shoppers categorized by their browsing and purchasing histories. Movie groups by ratings assigned by movie viewers. And that's how we can make groups. And that's what we actually happens in reality in data analytics, in machine learning. This method is very popular, and that's why when uh, you see specific genre of movies, you see when you shop through Amazon or through other websites, eBay for instance, you see some type of uh, categories popping up in a way that they somehow refer you to do those particular shoppings. And why they do so? Because they know your browsing history, they know your purchasing history, and somehow they are referring you to that particular type. So these things are also in practice we see a lot in practice. That behind those uh, their assignments, actually this unsupervised learning algorithm is going on. Principal component analysis. So principal component analysis, we call them in short PCA. The PCA produces a low dimensional representation of a data. You have a huge data, but you are not interested in that huge data. Since some of the variables, if not all, then some of the variables are correlated with one another. So what we do, we produce a lower dimensional representation of the data. And it finds a sequence of linear combination of variables that have maximum variance and are mutually uncorrelated. So those linear combinations of all the variables, they will be representing a maximum variance in the data. But yeah, or and the other hand, they will be uncorrelated entirely. Apart from producing derived variables for use in regression or classification, PCA also serves as a tool for data visualization. And we will see immediately how can we use PCA for data visualization, for instance. So PCA refers to a process by which principal components are computed. We call them principal components. And the subsequent use of these components in understanding the data. Right? When faced with a large set of correlated variables, principal components allow us to summarize this set with a smaller number of representative variables. That's what I described earlier, that collectively explain most of the variability in the original data. This is the idea. So you somehow reduce the dimension by keeping maximum variability in the original data. PCA is an unsupervised approach, as we saw, since it involved only a set of features for X and no associated with response Y. Apart from producing derived variables for use in supervised learning problems, PCA also serves as a data visualization. So it's some kind of repetition, but for you to remember these ideas. And principal component regression is also one of the remedies to the problem of multicollinearity. So if you have data with multicollinearity or predictors with multicollinearity, then you should not use linear regression immediately. Rather, you should use principal component regression. Yeah, it finds a low dimensional representation as we discussed, and uh, the idea is that each of the n observations lives in p-dimensional space. You have p-dimensional variable, you have p variables, so to say, p predictors, so to say, but not all of those variables are equally interesting. So PCA seeks a smaller number of dimensions that are interesting as possible, and where the concept of interesting is measured by the amount that each observation vary along each dimension. So it's kind of mathematical way of describing things in words, uh, but the idea is that since all of them are not equally interested, some of them are more interested, some of them are less interested. So why not use a linear combination of all the variables and find out a way with less number of observations or less dimensions, so to say. So the first principal component of a set of features like x1 to xp is a normalized linear combination of the features. So now you have written all the variables, all your x variables in terms of a linear combination, right? And that linear combination we call the first principal component, we call them z1. This linear combination has the largest variance in the data. And by normalized, we mean that if you squared all those parameters here, lambda 1, 1, lambda 2, 1, lambda p1, and then sum them together, this will be equal to 1. So somehow this is standardized, somehow this is normalized. And the elements lambda 1, 1 to lambda p1 are referred to as the loadings of the first principal component, right? And the constraints on loading is defined so that their sum of squares being equal to 1, since otherwise setting these elements to be arbitrarily large in absolute value could result in arbitrarily large variances. And that's why we do the normalization. Somehow normalization helps us to control the loadings, and also to understand how variation is actually, how those variables are equally are associated, how these variables are weighted actually. The proportion of total variance explained by the jth principal component will be lambda j, right, divided by all the loadings, the sum of all the loadings together, like here. So the population size, uh, pop or population size, and ad spending for 100 different cities are shown as purple circles. So you have population and you have spending on advertisement. So these are the purple circles. The green solid line indicates the first principal component. This line is the first principal component, and the blue dashed line indicates the second principal component. Always recall the point I made, that they will be uncorrelated with one another. It means they will be orthogonal. They will be perpendicular to one another. Principal component 1 will always be perpendicular to principal component number 2, and they both will be perpendicular to principal component number 3, and so on. So they will be uncorrelated with one another. Yeah, some maths here about the computation of principal components. You don't need to worry about them. SPSS will do the job for you, but if you are really interested, you can somehow understand what's going on behind. Suppose that you have n by p data, means n number of observations, and you have p predictors, and we are only interested in variance. So we assume that each of the variable x has been centered to have mean 0, right? This is very important. You need to somehow demean the data. Somehow you need to standardize the data before running the principal components. Then we look for the linear combination, and this will be a largest variance since we are talking about z1, and for each x1 has mean 0, so does z1. So like all of those, since all of them has mean 0, so this guy will be having mean 0 as well. And the sample variance of this guy will be written as just a squared sum, because mean is 0, and then divide by the number of observations. So what we do actually, we somehow use the linear combination, we squared it, summed across all the observations, the number of observations, and divide by the number of observations, and we minimize this factor subject to this condition. So if we do this optimization problem, then we get lambdas. So somehow the lambdas are achieved according to this condition. So this is a way to somehow evaluate lambda, somehow estimate lambda for your principal component, for your first principal component, so to say. The loadings, they define a direction in a feature space along with the data vary the most. So those loadings define how data is actually behaving, and you will see an example very soon how we can interpret those loading values. If we project n data points onto this direction, the projected value are the principal component scores, like z values actually. Second principal component is a linear combination of again the linear combination that has maximum variance among all linear combinations, but it will be uncorrelated with Z1. So we will be keep defining the linear combinations of each variables, and that linear combination will give us each Z, Z1, Z2, Z3 up to so on. But the condition is that all those Z values, all those Zi's will be uncorrelated with one another. And this will give us another loading. For Z2, I will be getting another loadings, another parameter values associated with a second principal component or other principal component, so to say. So it turns out that constraining Z2 to be uncorrelated to Z1 is equivalent to constraining the direction of lambda 2 to be orthogonal to the direction of lambda 1, right? Because this is associated with principal number component number 2, and this is associated with principal component number 1. And principal component directions like lambda 1, lambda 2 up to so on are the ordered sequence of right singular vectors of the matrix X. In total, we can have that many principal components. So like n minus 1 and p is the number of predictors, so which of these values is minimum, this will give us the number of principal components we can have, maximum we can have for our data. For instance, if you have 30 observations, n equals to 30, and your predictor is 5, so it will be like 29 and 5, minimum of 29, 5 is 5, so you can have maximum 5 principal components for that particular example. Let's have an example to see how principal component can be used to explain or somehow explore data. So consider the US arrest data. I see that there's a spelling mistake. Okay, yeah, USA arrest data. Now it's correct. For each of the 50 states in the United States, the data contain number of arrests per 100,000 residents for each of the 3 crimes: assault, murder, and rape. So there are 3 crimes, and you know the data for 100,000 residents for these 3 crimes. And we record urban population, the percentage of population in each state living in the urban areas, right? So the principal component score vector have length n equals to 50 because you have 50 states, and principal component loading vector have n p equals to 4 because you have 4 variables. Now, PCA was performed after standardizing each variable to have mean 0 and standard deviation 1, one of the conditions for PCA. Here are the results. So first principal components and second principal components. By the way, these are principal components. So these values are actually, these values are actually the loadings. So these are the loadings of principal component number 1, and these are the loadings for principal component number 2, opposite to that. And these are states, the whole state, 50 states of USA, and here lies the 4 variable, right? So let's see what does it tell actually. Now, if you look back, the first 2 principal components for US arrest data, the blue state names represent the score of the first 2 principal components, like here. The orange arrows indicates the first 2 principal component loading vectors. Like those oranges are the loading vectors, and those blues are the state names. Go back. Now see what happens. Well, by the way, as I said, the first principal component, the loadings of the first principal component are mentioned over here, and the loadings of the second principal component are mentioned on the right side. Now you see that rape was with respect to the first principal component loading, which is over here, so the rape lies somewhere here, so like 50% or 50, if not percent, 0.50 was mentioned to rape with respect to PC1, and with respect to PC2, rape lies here. So almost like, what is the value? It's like 17. So for example, the loading for rape on the first principal component is 0.54, and for second principal component it is 17. So the word rape is centered at this point. So now you can see how you can somehow define the word rape in this graph. So there are, if somebody asks you to define the coordinates of rape, so it will be like 54, 0.54 and 17. And this graph is called the biplot because it displays both the principal component scores and principal component loadings together. Like scores mean Z values and also the lambda values loadings. Now here are the lambda values for murder, for assault, for urban population, for rape. You see 54, 0.54 and 0.16 for PC2. Notice that the first loading vector places approximately equal weight on assault, murder and rape. So 53%, 58% on 50, well, if not say percent, 0.53, 0.58 and 0.5, almost equal weight on these three variables, with much less weight on urban population. Hence, this component roughly corresponds to the measure of overall rates of serious crimes. Now, since you have three, it doesn't happen very often, but in this particular example, it happens that PC1 explains crime because PC1 has high weightage for crimes. And also PC1 put somehow similar weight for crimes, murder, assault, and rape. But very less, it describes very less variation about urban population. But if you look back on PC2, minus 41, 0.41, minus 0.18 and 0.16 are the weights for crimes, and 0.87, the highest weight, was somehow assigned to urban population. So I can say that the second loading vector places most of its weight on urban population and much less weight on other three features. Hence, this component roughly corresponds to the level of urbanization of the state. So now I had four variables before: murder, assault, rape, and urban population. But now I can pick two variables instead of four, which will be PC1 and PC2. And I can use their Z scores for PC1 and Z score for PC2. And I can say that my Z score for PC1 represents crime and my Z score for PC2 represents urban population. So instead of having four variables, now I have two variables, and they do have clear definition, clear classification. So we see that crime-related variables, assault, murder, and rape, are located close to each other. If you look back again here, so they are close to each other, while the urban population is up here, a bit further. It indicates that crime-related variables are correlated with one another, right? States with higher murder rates tend to have high assault and high rape rates, and that's what you see here. Like Maryland has high assault, and then Georgia has high murder rate is in this region in particular, for instance. And then urban population is less correlated with the other three. Now we move on further. The loading vectors and biplots suggest that states with large positive scores on the first principal components, such as California, Nevada, and Florida, have high crime rates. Can we see that from the biplot? So like California, Nevada, Texas, New York, Illinois, like this is a positive, and they have a high crime rate, for instance, because they, all of them, like all the positive somehow loadings or positive scores actually respond to that particular region, while states like North Dakota with negative scores on first component have low crime rates. Let's see and go. Let's go back and see here. So North Dakota is over here, negative crime principal component loading, and also like here negative 0.50, and over here again negative 0.10%. And also it's really far from those crime regions. It means this region is less, or this region has less crime, so to say, or less of these crimes actually. California has high score on second component, indicating high level of urbanization. If you go back and see, California is up here. So with respect to second principal component, it says 0.45 or 48. And for first it says something like here. So this is of course we all know that it's a bit urbanized. Mississippi is less urbanized. Similarly, states close to zero on both components, such as Indiana, have approximately average level of crime and urbanizations. Like here, if you say Indiana, Virginia, they are close to 0 with respect to loadings and also with respect to scores. It means they do not have high crime rate, they do not have a high urbanization, but a mild level of urbanization and crime rates. So you see such a beautiful example, and that's how we can classify this example with respect to principal components. Which state has more crimes, which region, how crimes are correlated, and how we can classify them into principal components, for instance. If the variables are in different units, scaling each to have standard deviation equal to 1 is recommended. Otherwise, you see something like that. So if they have different units, then definitely use them, scale them to have standard deviation equal to 1. If you don't do that, things will pop up like this, and you see it's really hard to somehow differentiate how to interpret results over here. Another important factor which we can somehow describe or somehow interpret with the principal component is the proportion variance explained. So the natural question once you are run with PCA is how much of the information in a given data set is lost by projecting the observation onto the first few principal components. We are not dealing with original values, original variables. Instead of 4 variables, now we have 2 variables. So the question is, have we lost something when we did this projection, right? Or in other words, how much of the variance in a data is not contained in the first few principal components? Like in this example, in the first 2 principal components, how much of the variation is lost? How much of the variation which we cannot cover actually? So to answer this question, we evaluate a guide known as proportion of variance explained, PVE, by each of the principal components. So what we do actually, we evaluate the total variance present in the data. Since all the data values has mean 0, so we can evaluate total variation like this. P are the number of variables, and then we evaluate the variance explained by each principal component based on their scores, like here, right? And once we are done with those 2 quantities, we just divide them, take a ratio of them, and that ratio actually gives us the PVE. So if the PVE sums, always PVE sums to 1 and it gives you a value between 0 and 1. So sometimes we display the cumulative PVE, like how things are actually accumulating, right? So in general, as I said, there are that many number of principal components and we are not interested in all of them. So what do we do? How do we decide how many principal components we are going to use actually, right? So what we do actually, we make a scree plot like here. So we typically decide on the number of principal components by examining a scree plot. So like here, so principal proportion of variance explained is over here on the y-axis, the PVE, and here we have the principal components like 1, 2, 3, and 4. And somehow we see the cumulative principal proportion variance explained, which is of course the total is always equal to 1, and PV and the principal components over here. So the rule of thumb is when you see a tilt, when you see, well, sometimes this scree plot is also known as the elbow plot. So whenever you see a tilt, like here I see a tilt, somehow a turn, so to say, and that turn explains, okay, here I need to use that many principal components I'm going to use for my data, or that many principal components will be sufficient. If you have 4 variables, then there is no point of using 4 principal components because there is no reduction in dimension. So we always try to use less than 4, say 3, 2, 1. How can we decide? Well, we can decide through this plot, and this tilt, like here in this example, gives me an idea that okay, 2 principal components will be enough in order to define maximum variability in the data. And if you look here, so first principal components explains 60% of the total variation, second explains 80%, the third explains almost 90% or 95%, and 4 explains the total. So if you consider the 2 principal components, you will be going to accumulate almost 80% of the variation in the data. If you go for the third one, well, that third is even better, of course. You can see 95% or 90%. So between 2 and 3 principal components I can use. This graph is not very clear. Sometimes you see a very clear picture with a tilt obvious to you, and also how the variations are actually expanding with respect to the principal components. We choose the smallest number of principal components that are required in order to explain the sizable amount of information, of course. As I said, this is also known as an elbow or a scree plot or elbow plot, and the turn in the elbow tells us how many principal components we should use for our data. So just read this slide. It tells us everything what I discussed with respect to previous graphs. Now we move on to another topic. I will briefly touch upon this topic, the PCA, the factor analysis, some historical beginning before we move on to the exact definition or what actually we do with this method. So it was developed by a famous psychologist, Charles Spearman, and the main rationale of the factor analysis was that if there is a single variable behind a group of variables which shows stronger correlation between variables within group than the correlation between the variables in the group with the variables outside the group, right? So you have lots of variables and you wanted to know which of the variables shares maximum correlation within the group instead of looking for variables outside the group. And so that is the idea. So you don't classify different groups, rather you look for one group, and within one group you look for a factor which is common to all the variables within that group, right? So that's how we do the factor analysis, and the question is to find a way to detect such groups and then identify a corresponding factor. So like here, he studied examination scores for a large number of students and concluded that the correlation between scores in different subjects showed systematic similarities. Like here, x1, x2, x3, x4, x5, s6 are the variables, and you see that some of the variables are highly correlated, some are less correlated. Like x1 is highly correlated with x2. Classics and French is very correlated because if you look for classical literatures, you are going to, of course, boils down to French literature or English, for instance. But maths and pitch and music are slightly less correlated, and so on. So Spearman suggested that each of the variables was composed by a journal factor common to all variables. And that factor, the key is to find that factor. So if you see here, x1 is defined by loadings, like a parameter associated with that factor f plus some error. X2 is also associated with the same f but with different loading, because x2 may be having a different structure associated with f. X1 may be having a different association with f. Similarly, x6 may be having a different structure with f or different relationship with f. F is constant in all of those set of variables, but those loadings are differing with one another. And the way those loadings are differing will explain how x is associated with f. F is a common factor, as I said, a journal talent skill level, so to say, and this is free to interpretation. And those L are loadings in particular subject. And epsilon, of course, represents subject specific skills, some errors, so to say. So in this situation, factor analysis tries to describe the structure of the correlation. There are a couple of spelling mistakes I can see. Describe and structure of the correlation between large number of variables in terms of those factors. We call them latent factor because we don't know them, right? And the idea is to somehow define or somehow discover that factor. Factor analysis is often regarded as dimension reduction techniques. Observed variables are regarded as generated by a small number of non-observable variables. I will skip this math in the final slide. I actually don't want to go into mathematical details, so let's skip those slides. Let's read those examples rather. So again, the same example. based on the, well, not exactly the same example, but based on the score of 6 subjects: Swedish language, English language, history, maths, physics, and chemistry, from 220 students. So we see a correlation matrix like that. And we will try to explain the structure in the correlation matrix as originating from 2 factors. So somehow we will have a data for 6 variables, and we wanted to somehow describe the overall structure in this data with respect to 2 factors, 2 common factors. So how can we do that? Well, so these are the loadings. Somehow these are the loadings of those 2 factors. These L associated with factor number 1, and these are the loadings associated with factor number 2. The important concept, by the way, I should mention here related to factor analysis is rotation. And rotation is a way to understand those loadings actually. So these are the loadings. Somehow we do some rotations to understand the loadings properly. And the loadings concentrated into few of the original variables. So these are the values of L with respect to each factor. Now if you see here from a graphical representation, I just plugged in all those values over here. So these are the values, 3 values associated with loading number 1 and loading number 2. Some were, you see, some were positive and some were negative. So I just plugged them up here. And also when I rotate, I see that all of those loadings are now positive, or at least most of them are positive. So rotation is like you just rotate 90% degree or 180 degree, things of that sort you can think. So now most of the loadings are now positive. Only one guy is negative. This guy over here is negative. Finding the rotation based on graphs is feasible only for the 2 and 3 dimensional cases, and there is a need for an automatic choice of rotation, and there are of course several criteria. One famous criteria is Variance criteria, and when you will be working with SPSS about this problem, you will see this over there. So here one tries to maximize the sum of variance of the squared loadings Li in the columns of L. By this L is a total matrix which is for the loadings, for loadings for both of the factors, you can say. And there are many ways, of course, to estimate factors. Of course, there is no obvious winner, but we choose loadings with respect to our ease to interpretation. If we see that some way of loading is easier for us to interpret, we just use them. So just go through those slides. There were a couple of mistakes in this some slides. So when I will upload them, I will fix them as well in the PDF files. Use them, read them, listen to the lectures, and try to understand, so that when you work with your project or your assignment, you will be able to do that on SPSS. Thank you.